Olivier has done his PhD at Ecole Polytechnique. He also has done a postdoc at Max Planck Institute in Tübingen. He recently did a lot of interesting work on deep generative models and on other topics. I think also some hyperparameter research. And he is here to talk us through some possible formalizations of representation learning.
Thank you. Thank you for the introduction. And thanks for inviting me here. Unfortunately, I did not attend all of this workshop because I was at another one earlier today, so I did not see all the talks. So apologies if I say something that is overlapping with what other people have said or contradicting. So the goal, because it's a workshop, I thought it's a good opportunity to raise questions rather than present results. So here I just want to kind of brainstorm, and hopefully that will lead to some discussion later on, maybe in the afternoon panel discussion about what is representation learning and whether we could formalize it in the same way that other, supervised learning has been formalized, for example. And not that I think that theory is the only way to make progress, but I think it's important to ask those questions. Maybe there is no answer. Maybe we just fall back to saying, well, there is no precise way of defining those things, so we just have to use heuristics and follow our instinct. That's fine, but at least we should ask those questions. So I will, basically talk about three things. One is, what is the goal of representation learning in my, personal opinion? And of course, this is up for debate and you can disagree. I will go through certain approaches for representation learning and then go into how to formalize them. Although this, there is no final formalization, it's more like directions of possible exploration that I will propose. So, okay, so what is a representation and what is useful for? Why do we even care about representation learning? What do we do with a representation if we add one? And how do we even recognize one? So to answer those questions, I want to start with a bit of history. I think this quote by Vatnik was mentioned by Larry earlier on Tuesday, I think. And I think it's interesting to see that, well, at least for those people that were in machine learning at the time, so that means like only the older ones, this kind of led to the belief that we should not care about the structure of the data. If we want to do, say, supervised classification, we should go straight to trying to learn a classifier, forget all the generative business, right? Like, don't try to model your data because in a way you don't care. You just want to say a classifier that tells apart the positive and negative examples. So why do you need to model the structure of the positive class and the negative class, right? So that's a bit how it was interpreted. In practice, it was not really. So it was interpreted as, well, use discriminative models, forget generative models. In practice, that's not quite how Vatnik wanted to or intended it to be used, right? Like, it was more a justification for him about using, looking at the transduction problem instead of the induction problem, meaning that if you have a bunch of labeled data, unlabeled data or test data that you want to label, maybe you can use directly those data instead of trying to build first a model that would predict at any given point. Like, you can just try to predict at the points or at your test points. That was the intent, but it was it got interpreted more in that way. And that led to, basically, at least for theoreticians, led to neglecting this idea that the data itself, like the input data, right, can contain some structure and that this structure is useful. And now, you can see that there is a bit of a comeback with, deep learning is one example, but auto-encoders, generative model, these are all approaches where fortunately, the structure of the data is considered, a first-class citizen in a way. So, and basically the question is, does it make sense, right? Does it make sense to follow that guidance of Vatnik, or should we take a step back and say, maybe we humans don't do supervised learning, and that's why, like, although if you want to do just supervised learning, maybe you can forget about the data structure, but maybe that's not how human learning actually works. And I have another quote here, which is from a blog post of Giorgio Patrini, which basically says that, right? Like, if you think of what we do as humans, it's not really that we have like zillions of examples that we are trying to, create the label of. And I think this is something that maybe representation learning is going into the direction of trying to model. Okay, with that, let's take an example. If I ask you to draw a person, so like, what would you draw? Right, like try to think in your head, and I think like this characterizes or is a way to characterize what is your representation of a person, and I think what would happen is you would not do something like this, right? I mean, this is very hard to do because, or like to paint or draw a person with all this level of detail requires, a lot of time and a lot of effort. So that's not how you represent persons in your head. At least that's my claim. It's more like this. Actually, I cheated because these are not from kids. That's my drawings, but I took inspiration from the drawings of my kids. And actually, what's interesting, I did study those drawings quite a bit because it's interesting to see that. What are the salient features of those drawings? There are essentially two kinds of people drawn by kids, like the bodiless and with body, right? Like either they completely forget the body, they keep in mind that, well, a person is essentially a face because that's how you recognize a person. And then it has some, limbs because that's useful, right? And maybe those limbs actually, sometimes you see these like a large number of digits, not digits, fingers, sorry. Like it's very rarely 5 fingers. It's often a lot more. Because, I think again, this is, modeling the object based on what it is used for. And, like kids know that hands are very useful. They don't care about the toes. Usually, but hands are very useful, and the fact that you have fingers, and actually if you could have even more fingers, that would be so cool. So that's why at least that's my interpretation. So what I'm arguing here is that representations have certain properties, and basically I'm trying to summarize them here. I mean, because what is fascinating is that despite the fact that this is how kids would draw a person, they still are able to recognize their mother, say, or any person in their family very accurately, right? So even though they can only produce that, they have in their minds something much more rich, right? And yet they cannot paint that full representation because first it would take a lot of time, it would require very advanced motor skills, but I would argue that even if you were to use someone and you were to describe to someone who is an expert at painting pictures, like you would not be able to convey enough information to reproduce like the full extent of all the details, especially the body, right? The face is something that we are very used to remembering, but the body is something that you very often don't even remember. How is the body of your mother? I mean, it's hard to describe perfectly. Right, and so basically my point is that the representation has these kind of properties, like it's useful, right? It's based on what you will do with it. The fact that, with that representation you understand that the person essentially can do certain things, and, like if you see a door, you can tell whether a person could go through that door or not based on the size of the door or things like that. It's simple, right? Like you skip a lot of details, and yet it's still accurate enough to recognize and identify novelty. Like if your mother has glasses, you would notice immediately. Right, so now, okay, why would we want to reproduce that? I guess now we're talking about, like if we were to build a machine that is able to produce such representation, what would it be useful for? And there are like different applications of this representation learning. One is, the classical one is to learn transferable feature. You learn on some task and you want to then use those features on some other task, or you want to learn from different corpora, which is also something that is rarely done in practice of machine learning, but that's probably, like, you learn how to recognize objects independently of how you learn how to drive a car, right? Even though, end-to-end learning is very popular, that's not how humans learn, I would claim. And then, that also understanding the representation can help you understand some specific properties of your data. And, well, how would we evaluate success? Probably we would do something like visualize the representation. That's what people typically do. But ideally, we would want to measure certain properties. There has been some proposals for measuring certain things like disentanglement of the representation. And then you want to measure the success of your representation on tasks. Okay, so now, this was like very philosophical introduction to representation learning, but now let's try to be a bit more concrete. Okay, like if we were to define what is a representation, then this is a simple definition. You have an input data X, and you want to map it to some other space Z, and basically Z is the representation of that input. Let's say the input is an image, and the Z representation is a vector of numbers. And you have basically two ways. Either you try to build that direct mapping from the input to the representation, or you can try and learn the inverse, like what kind of object you would produce given a certain representation. And then typically, okay, like imagine that our goal now is to learn those functions, either f theta or g theta. Let's say it's parameterized by a bunch of parameters, like it's a neural network or something. We want to learn those things. So we need to define a criterion to optimize, right? And there are many ways to do that. And like the point is to introduce a goal so that you can, optimize that goal, and that will give you guidance to find the right network parameters. Typically, people use supervised learning as a goal, right? Like you first learn your features, and then on top of your features, you do classification, let's say. Or unsupervised, like you don't really have a goal in the sense of a target label to predict, but then you invent some ways you create your own goal, and I'll get back to that. Or sometimes you want to first build a representation and then kind of measure it or use it to do supervised learning on a separate data set, or you want to do transfer learning. And one way is to see all these things as like these are not the ultimate goals, because the ultimate goal again is to build a representation, not to solve those problems, but they are just constraints or ways to guide that search for the representation. So again, we're deviating a bit from Vapnik's guidance of not solving an intermediate, a harder problem on our way to solving the final problem. To be more precise, right? Like in the supervised case, you also learn a classifier. You learn your representation function f theta, and you also learn a classifier c phi, which maps your representation to labels. And usually you jointly learn those two things. Or in the unsupervised case, you have the direct or inverse. So in the direct case, you try to reconstruct, say, the data. And in the inverse case, what you build is just some function that takes a representation, maps it to a real input, and you compare that to an input, and you compare that with real input with some measure of distance between samples, and that's what you minimize. And so on and so forth. So one interesting concept is this idea, like if you're in the unsupervised context, is this idea of self-supervision. Basically, it has to do with you don't have labels, so you invent some labels, and then you have a supervised problem. And this is typically done by hiding a part of the data and trying to reconstruct it. So either you may want to reconstruct the whole input, the whole image, let's say, or you reconstruct a part of it, like you hide, say, a certain patch of the image, and you try to reconstruct it. That gives you a supervision to train your representation. Or you can, like, instead of just hiding some inputs, you can hide some properties of the data, like you can take patches of your image and shuffle them, like put them in a different order, and try to, from those shuffled image, recover the true image. So now you have all the pixels, but they are in a different position, so you have to recover that. And and so that gives you some supervision. And now, like if you look at specific examples, like in language, obviously the well-known technique is to try and predict the next word. In image, that's what I was mentioning before, predicting a missing patch or the order of the patches. In games, you have this idea of self-play, which also gives you indirect supervision by playing against yourself. Or in reinforcement learning, you can invent auxiliary tasks. Say you have you want to navigate in a maze. One auxiliary task could be to try, like independent of the reward that you would get by navigating that maze, you may want to invent a task which is try to control, say, some pixel on the image, right? Like if you want to apply a certain action such that the image changes in a certain way, let's say moves to the right. So you will learn like what action leads to that, so that gives you a supervision, and that supervision can be used then to learn some representation, which eventually, essentially in that case, a representation can be seen as the first few layers of your network that you will share with other when you use it for other tasks or for the final task of optimizing reward. Okay, and so now, like, okay, these are specific to certain problems, but now there are also techniques that are generic that you can apply, always, independent of what the nature of your data is. And typically that's the auto-encoding approach, which is you just try to reconstruct the whole input. You don't worry of trying to hide some information. You just take the input and reconstruct it, right? And so, well, you can view it probabilistically. Your representation function can be non-deterministic, and then and from that from the representation you try to build also another non-deterministic function that predicts the true input, and you minimize the log likelihood. Well, I guess maximize. Sorry. And of course, yeah, you can say, well, in this case, why don't you just copy the input? And that's when, like, obviously for this to be meaningful and to produce anything interesting, you need to do some regularization to prevent the system to be able to just learn the identity. And there are many different ways to do that. One is to constrain the dimensionality of your representation, or introduce some sparsity regularizer, or introduce some prior. That's the variational autoencoder, or VAE, or beta VAE. Or yeah, you have different forms of this prior. There is also the so-called Wasserstein autoencoder or adversarial autoencoder, which has a slightly different form. You take the expectation inside, or you can have some, like in factor VAE, you can have independence favoring regularizer. But the point is, like you have to fight against the fact that you want to skip details, right? Like to have a meaningful representation, as we said before, you want to skip details. Now, if you want your representation to be such that you can reconstruct the whole input, then you're not really skipping details. And you introduce this artificial constraint on the way, but you still are trying to reconstruct all the details. So it's hard to know which details are important or not important. So that's one downside of this approach. Another thing to note is that a lot of the classical techniques can be viewed in that view of autoencoder, like k-means or PCA. That's essentially autoencoders with specific functions, encoding, decoding functions. And then you have like I was saying, the inverse self-supervision, where now what you're learning is not a representation map, but a generator from the representation to the input. And then you define a distance between two sets of inputs, one which is fake, one which is true. And well, there are like essentially two, but probably more example of that, MMD and adversarial or GANs, which use different ways of measuring the distance. And those, like measuring the distance, involves kind of finding a maximum over a class of function. And basically you have different class of function, that's the only, and a different loss, but that's more or less the only difference. What's interesting is that often this maximization problem here is done over, well, a neural network, and that has certain advantages because you have additional regularization brought in by the using of a deep network, as opposed to maximizing over the whole class, for example. Okay, so now let's move on to how do we formalize all this, like the idea is to try and copy what we know already of formalizing learning in different contexts, like in the pack learning, supervised learning context, where you assume you have an unknown distribution and you get sample from that distribution, and then you can either look at it from the point of view of a given class of function, and you want to see whether you can, with a certain algorithm, recover the best in that class of function, or you're given an algorithm and you want to say something about this algorithm, whether it's consistent, how fast it converges, and so on and so forth. So the question is, can we phrase those questions in the representation learning context? Yeah, that's just to say that I will go through the different setups that I mentioned before. So let's start with the self-supervised one, like the encoder-decoder or auto-encoder framework. So there is this definition actually, which is due to Elad Hazan and Tengyu Ma, where they basically say, well, let's look at it from the point of view of a class of pairs of function, encoding, decoding, or you can also apply that to the learning representation in the supervised setup, where the decoder is a classifier. That's the same thing. And then they define learnability of that class by the fact that you can approximate well the best combination in that class, right? So if you take, say, PCA, where the encoder is a projection and the decoder is, is another, like is the adjoint of the projection, then the question is, can you find the best projection in the class based on a sample up to some epsilon? And there is a constraint which is like it's k learnable if the dimension of the representation is bounded by k. And actually there are some results that have this flavor already. So in particular for PCA or kernel PCA, and some other like relatively simple algorithm. But unfortunately there are no extension of these things to, at least to the best of my knowledge, to autoencoders. So it, like we have such statement and result in that framework which characterize the learnability and the convergence rate only for very simple classes of functions, and not so much for more interesting autoencoders. So I guess that's one direction I would spell out as an interesting direction to explore. But I think what's important is that, like, even though it seems like we have a framework, it's still very preliminary, because there are lots of questions that are not even, we don't even try to address yet in that framework, like what is the base optimal pair, right? Like how do you define the constraint on the representation? Like do you say, well, what is the best given a certain number of bits or a certain number of dimensions, and what would be like a minimax algorithm in that context? So there are lots of these questions that are not even phrased yet, which I think we should start with. And in the adversarial case, basically you have more or less the same. You can more or less see it the same way, that you have two classes of function, right? The class of the generator and the class of the discriminator. So you can also play that game of saying, let me limit those classes of function to be certain predefined classes, and let's see whether I can reach the best in that class. But then it's like what you want to do is not to compare to the best pair in the class, but to compare with the best pair given the optimal discriminator. Because the interesting thing in the adversarial case is that if you look at the optimal discriminator, it gives you usually like an F divergence or a metric on the probability distribution. So that's the kind of thing you want to compare. I mean, okay, maybe I won't go into the details, but you can also phrase certain kind of learnability in that context. It's a bit more delicate to like I need to introduce more notation, so maybe I'll skip it, but just to say that you can also use similar kind of framework with a given class of function over which you optimize for certain cases. And now let me finish with two, maybe like that's even more in wavy than what I said before. It's more like giving a direction again. In the case of semi-supervised representation learning, which is where you try to build features first on some data, possibly unlabeled data, and then you want to use that representation to predict or to classify, but you want to use it, you want to guarantee that you will use as few label points as possible to reach a certain error. So you could formulate it as, you know, how well is your representation able to reach a certain error with a minimal number of labeled examples. And then in this case, you would have three classes to consider: the class of the encoder, decoder that you use to train your classification, and then, your representation, and then the classifier that you use once you get the labels to do your classification. And in the case of multitask or transfer learning, so there is this idea which I would like to explore more, which I think is interesting, which is to formalize the fact that you may have multiple tasks that you want to do well against, right? Like, so you imagine that you have a class of possible tasks, that from that class of possible tasks you sample, let's say, k of them, and now you want to build a representation that will do well on all k of them. And so that means you have to assume something, because of course otherwise it doesn't make sense, but and what you would assume is that you can factor all these k tasks in the sense that there is one representation function that will allow you to do well on this k task, meaning that once you have this representation, those k tasks can be expressed by a simple classifier, let's say a linear classifier. So you can say, I have this class of complex tasks, I take k of them, and I assume that I will be able to build a representation such that all the classes, all the tasks can be represented by a linear classifier. And then, understanding in which cases this is possible, I think would be interesting to understand the power of multitask learning. And with that, I will conclude. So basically, yes, like as I was saying in the beginning, I did not give you many results, but it was more like an attempt to phrase a certain number of questions regarding formalization of what is representation learning. There are some early results in some cases, as I mentioned, but there is still a lot to explore, and especially in the later cases of semi-supervised and multitask learning. Thank you.
I think we have time for one or two questions, but maybe Yasha can already start to set up. So do you have any questions over there?
Thanks, that was really good. I wondered if you had thoughts on the role of asymptotic theory and how asymptotic theory may help us do certain types of analysis, particularly against semi-supervised learning. Because it's one of the things that, even though the entire text was written on it, we don't actually look at it anymore, but there is a lot of insight. The thing that I'm thinking of particularly is when we look at GANs and we see all these shipping penalties which are coming up as graded penalties. And when we look at the graded penalty, they look exactly like the thing that is minimizing the asymptotic covariance of those functions when you take it in the asymptotic. And I wonder if there's any other sort of thoughts, references, papers that you think which may be useful for us to think about, to try and address the questions that you're saying. Thanks.
Yeah, so it's true that, there is a lot of literature on asymptotic theory for like supervised learning, which I guess my point was that we can import some of that knowledge. Now, of course, you should take that with care, or with caution, because sometimes, it doesn't really match with the way we use those algorithms in practice. Like, we never have infinitely many data. So, interpreting these results requires some caution to understand when they can be applicable and what they tell you about your algorithm. So I think that it's not so straightforward. But I think what you're saying about the asymptotic covariance, I think the talk recently, I have to remember exactly the title and details, but where basically the point was, if instead of looking at convergence rates and like standard minimax theory and so on, you look at the asymptotic variance of a particular algorithm, then the structure of that asymptotic variance can give you insights into what you want to regularize your algorithm with. So I think the point being that there are two different goals, right? One is you want to prove something about your algorithm, and in this case you need to have some sort of convergent bound rates or stuff like that. The other goal may be not that you want to understand or prove something about it, but you want to get insights of how to modify it to make it more efficient. It doesn't matter that you have a bound or a theorem, as long as you have some understanding of the behavior of that algorithm and how to improve that behavior, that's sufficient, and the asymptotic analysis of the variance or covariance of the algorithm can be a hint in this direction.
Okay, thanks. I think we need to continue.